one more thing I forgot. Okay. Next Monday we have a first items workshop of this year, of this fiscal year. Next Monday. I think 4 o'clock. Then Tadashi Takai will speak on information, quantum information, and then space-time geometry or something like this. So that should be very interesting. It's one of the most famous guy in the world, I would say. So you should come.
Yes, thank you very much. And so let me make it more larger for the Zoom audience. Okay. All right, so let me start with this famous line here. And that remark was made like 600 before common era by a Cretan philosopher, Epimenides of Knossos. And supposedly he remarked that all Cretans are liars. So what prompted him to make such an accusation on his own people is not known. But we know that poses some conundrum. So this, if you say that Cretan says all Cretans are liars, then he may be lying as he is a Cretan himself. Then that statement is true. So it's really difficult to make which this sentence is true or not. It's not more clear if you write that this sentence is not true. Okay, so can you prove this sentence is true or not? So this is the same structures that you have encountered. So at the core of this, maybe we have a paper. Okay. So at the core of the paradox is self-difference. Self-difference is a statement that refers to the sentence itself. And self-difference tends to lead to the paradox. Here, this actually causes some paradox. And this type of the paradox is called the liar paradox. Okay, so the liar part is referring to this Epimenides remarks on his own people. So that is sort of the paradox in a semantic sense, but it's not limited to the semantic paradox. And let's consider Russell's paradox. Okay, Russell's paradox is how it works. So if you define certain set as all sets that are not members of themselves. So this is the set you define. Certainly you can write this kind of sentence or the definition. But here comes the paradox. If X R belongs to themselves, well, if R belongs to this, then by these definitions, that should have these properties, X is replaced by R. So it kind of contradicts the suppositions. On the other hand, if R is not part of the members of the R, then that qualifies as the member of this. So that either way, you have some contradiction. So it may be my prejudice, but when mathematicians encounter such kind of statement that they cannot prove, so what do they do? They usually resort to the actions. So they just simply say that if you cannot prove certain sentence, they make it some actions. Or just take the axiomatic system that exclude the such nonsense sentences. For the set theory, you can construct, for example, Cermero-Krenkel axiomatic system that the I is not a part of the set. So that is usually done in this setup. So everything is fine. So you have some paradox. You just come up with a clever axiomatic system. But it's not really the end of the story. So here, enter Goedel. And achieve incompleteness. Goedel's incompleteness theorem tells us that whatever you come up with a very clever action systems, there will be a certain sentence. You cannot prove or disprove within that axiomatic sentence. So the core of his proof is actually self-reference and the liar paradox. So Goedel proved that there's something sentence like self-reference and with a similar structure of the liar paradox. So there is some certain sense, like a structure you cannot prove. To go into details, let me introduce a kind of equivalent formulation to the systems. That was also introduced by also famous mathematician, computer scientist Alan Turing, and his folding problem. So this is the intent. So folding problem asks that if you have some Turing machine, you can consider Turing machine as a simple computer you are using this. And if you pick up some certain program and data space, you put it in the Turing machines, there is no algorithm that judge this Turing machine will finish the job and kind of stop in finite time, or continues to run indefinitely. So this is the sort of the problem, and it means that make some correspondence with the Goedel's incomplete. So if you usually have some sentence, you have some logic systems, and you get some result. On the other hand, you can judge by the sentence with some axiomatic system, and you get it to or false. On the other hand, to folding problems setup, you start with some certain program, the data set and put it in the Turing machine. And we get some outcome. Outcome means including the result that you have machine running forever. And Turing is asking is there any faulting algorithm? Or in that it's wiggling room, you can call some programs. That judges, before put this program data in the Turing machine, judges its fault or done forever. Okay, so it seems very innocent that you could write down very clever program that you just you are shown the data and the program in front of you and judging this program will hold or run forever. However, if there is such a we should have some
8 or 9 weeks.
Yeah, I realize that we should have a very clock down there. So, okay, so it appears to be there's no problem. You could in principle have such an algorithm. Yeah. However, suppose you have such an algorithm and write a program that checks a certain number theory suppositions, like to imply number conjectures. So you check and find the first k set of those kind of twin programs and take k to make it larger indefinitely. And you put the program in this faulting algorithm, and if it judges it will fault or it runs forever, then actually it's kind of determining this twin prime conjecture is true or not. It's same for the Fermat's theorems or collapse conjecture or other certain kind of number theory conjectures. You can check one by one. So this could be some kind of meta theorem, sort of. You can check any conjecture. So this is really something extraordinary thing happens if there is some faulting algorithm. So we usually just throw everything else and constructing faulting algorithm. Then we get most of the number theory theorems. But well, if it works, does it work? It's not really. So luckily, Turing saved us this futile effort by just thinking that there will be no kind of no algorithm, such an algorithm. So this is the Alan Turing's contribution, and this is equivalent to the proving the incompleteness theorem. So this proof, I'm going to sketch this proof, and this is sort of education. So the proof was counterexample. Okay, so we start like as a program A and the data X, and we have some Turing machine. and you have some outcome. So suppose there is a millenia-old input. Then algorithm. Program. So that H takes a program and takes an input. So that works as something like that. That we give back true if X false. If X does not hold, then forever, then it's gives back the whole. So that determines if the set of the X is true or false. Okay? However, we can construct another program. Yeah. And it takes input some programs. So those are programs. And you can make MA runs forever if HA is true. Okay, so I just wrote that HAX, but here H algorithm takes A as the input data. And MA is then AA is false. That's kind of simple. If you have an HAA is true, then you put it into the infinite loop. And if HAA is false, then you terminate, stop the program immediately. So that's simple. So this part is not really a program. Here, this H is put on the A and A. Okay, so now the question is, then if MM false or not? Yeah, that's a big question. So if MM holds, then HMM is false. Then by definition, this is MM, not false. Remember the AX, the construction, the true and the false is X false and X not false. And the same goes to the M not false. That means HM is true. Then MN to the false. See, the structure is the same as the Raya power. So if you start with some kind of make a supposition about the supporting point, then you lead to the quadratic outcome. So in this sense, there is some always you can construct the MM rotation. You cannot prove what is true. So in this sense, faulting problem is undecided. is said to be undecided. So this is a statement. You can always write something like this. Okay, so I've done another time, so I don't have to go to the details, but I wrote these references. Those are physics papers. And what have they done is kind of make some physical mapping the physical system to the Turing machine. For example, a kind of near-stable Hamiltonian lattice or finite quantum system, or using statistical scale, he made a two-dimensional supersymmetric model, which can be mapped to the Turing models, with if there are certain physical criteria, it corresponds to all the Turing machine holds or not hold. In this case, there is a gap. If the system is gap, then it holds. In this case, certain system is harmonized, Turing machine will hold. And the Tsukasa case, if there is a supersymmetric vacuum, the system stops. So if you make that thing, always there is corresponding to the this step out, which cannot be decided by this would-be faulting problem. So in this sense, they claim that the problem gap in the spectrum or harmonization or existence of supersymmetric data is undecided in this sense. So that's very nice. But they claim to have some more physical constraints. But this is very unclear. But there seems to be a lot of them to if make it really physically serious constraints or not. I think was further investigation. Okay, I stop here. Thank you very much. So, any question? Yes.
So I choose the last point. Those because they constructed some Turing machine type physical system, and then what they do? What they have done?
They constructed a certain setup, but that's really difficult completely say. You construct a physical model, like writing a Hamiltonian or some superpotential, and make it possible to chat each corresponding to if the system has a gap, and then corresponding Turing machine and maps one-to-one about the calculation of the Turing machine, and so that it makes stops. So they have some variables and kind of parameters, and you can test different parameters. So, and when you hit a parameters correspond to this one, this self-referring statement, then this judging faulting algorithm fails. So there's a thing they are saying that so there is no way you have some algorithms that judges all those systems have a gap or some supersymmetric data does not exist. You can check one by one, but there is no way you write down algorithms. All those possible models for all possible models be judged by just one kind of algorithm. So this is what they claim.
All models mean the same model but with different parameters.
There's different parameters.
And whether depending on the parameters, whether it's gap or not.
No. Well, it can be determined most of the case. But when that faulting algorithm hits this this sentence, then it becomes contradictions.
How robust is the Turing machine encoding the errors in the model or in the draft?
Oh, there's no error is assumed. So
yeah,
it's strictly logical.
So I can see that in principle, this is a very nice way of getting an undecidable problem. But if you were to try and get physical consequences, somehow you want the encoding to be robust to small errors.
Yeah. So we think that one. Yeah, that's a good point. So that's why incompleteness theorem is so powerful, because there's no margin of error for their losses. But in reality, you have to introduce some errors. So that's I think good point. I completely agree with you. But here, actually, it's not really a physical consequence. It's discussed. But some authors kind of implicate that there's some physical consequence. But I have some doubt. Well, one reason is what you just said is margin of error, and they don't really argue about this ordering algorithm part. They rather kind of this is really a difficult problem, so that you can construct something Hamiltonian systems that correspond to the actually these physical consequences, gap or gap systems, or let's say supersymmetric data. So it's really kind of involved work here. But so the essence is that the self-reliance statement and all this Turing machine setup. So the whole program is undecidable in the sense these people make working down these certain physical systems, trying to find out this is if gap or supersymmetric data or summarized. There's no kind of takes the whole algorithms, and they eventually fail at a certain point. So that's the I must say about that.
I'm keeping this conflict in Cretan based on Cretan that I mean it's always based on whether it's either true or false, or one or zero. Can you generalize this one to the some probability few false? Like quantum mechanical setup, and then still give you false or not?
Yeah, another good point. That's also I thought that possible room for this. But I don't think there's no mathematical attempt to that this kind of stuff. Even some quantum logic, it's really not really quantum in the sense. You always get the same result when you put it into action. If you introduce some probabilities and one sentence you put in, sometimes it gets true, sometimes it's not true. I'm not sure if you can construct the mathematics based on this kind of logic. I think nobody has tried, I guess. Yes?
Yes, I actually have two questions. So the first question is that if you want to apply this to physical system, and is it possible that given any kind of physical system, you can always construct this kind of Turing machine algorithm?
Oh,
is there any criteria for that?
It is really involved procedure, so I think that could be very limited, and so you really have to contrive that that putting together a different part of the Hamiltonian to make some interactions is very contrived way. So I don't think it's really practical to do that, or even in the real experimental settings. But still, if we don't know, you could do. But so far, it's really difficult. Okay.
And yeah, the second question is follow-up. So once you have a system and you have a Turing algorithm for that, does that mean that you can always define that kind of MLN, which in some sense you can somehow identify some physical quantity which is not which is undecidable?
Yes.
Okay.
It's not a yes. This is not really a physical quantity. It could be some quantity or just a parameter for certain systems, which is described by H as A. And those are very huge numbers. So in principle, you are reading those programs or kind of definition of systems as the numbers, which is sometimes kind of in the connection with the Gödel numbers. Gödel's proof, he just made these procedures with just one number. And you can also do the same thing. Your computer program, you just print it out, then these are just a number. These are the simple digits. Then you can read as a number. So you can think about this as everything as just a number, one number. However, it's large. It's really large, but it's just a simply a number. So that's the kind of beauty of it, using the Turing machines. And you don't really have to. If you kind of make a setup, just a simple number will give you something. And so you can explore numbers indefinitely until you hit this ML. And eventually it should come because there are certain numbers. So sometimes they use some really subtle point, but eventually it's guaranteed you will be the right program you wrote as ML. Okay. Any other questions? Okay, no further questions. Let's terminate this 10 minutes talk. Not really 10 minutes, sorry. Okay.